So let's talk about finding the derivatives of inverse trig functions. So first, let's have a little bit of review of what an inverse trig function is. So the inverse sine of x equals y is the same as saying the sine of y equals x. So remember, you're looking for the angle whose sine gives you that x value. That's what the inverse sine is about. The inverse sine, remember, we're going to restrict the sine function down to negative pi halves to pi halves, because otherwise it just keeps going over and over and over again. It's not one-to-one. So we're going to restrict it down to a one-to-one section. We do minus pi halves to pi halves because then we will get negative sine values, negative x values and positive x values. So we get both. That also means, by the way, that x can only be between negative 1 and 1, because remember the sine can only be between negative 1 and 1. All right, so let's evaluate some. So let's do a little bit of evaluation here. Let's remind ourselves about it. The inverse sine of negative 3 halves. So we're looking for some angle that when I take its sine, I get negative 3 halves. So think of your unit circle here. So remember, this would be pi over 3 has the x and y values of 1/2 and square root of 3 over 2. Remember, the sine is the y value, but this is not negative. We need the negative one. And so remember, we also have down here, but that's not where we want. We're going to be from negative pi halves to pi halves. So we're actually going to be down here and up here. So we're actually looking at this angle here, and this is where your negative 3 halves would be, because your y, you want your y to be negative. So we're going to be between negative pi halves and pi halves. And so that would be this angle here. That would make it negative pi over 3. We want the cosine of the inverse sine of 1/4. Well, that's a little bit more work. We'd have to find the inverse sine of 1/4, but 1/4 isn't one of these on our unit circle. Remember, the other one up here would be square root of 3 halves and 1/2. The one in the middle is square root of 2 over 2 and square root of 2 over 2. So, and then these are, of course, 0, 1, and 1, 0. So we don't have 1/4 up here. So we got to find another way to do this. So what I want to remind you is that the inverse sine is an angle. So we're looking for the inverse sine of 1/4 equals some angle, which means that the sine of A is equal to 1/4. Well, let's go ahead and look at a triangle, because it helps look at triangles. That's really where we were introduced to sine and cosine functions, with triangles. So we have a right triangle here. Here's our angle A. Remember, the sine of the angle is the opposite over the hypotenuse. So 1/4 would mean 1/4. We don't have to be a unit circle, so nothing says that the hypotenuse has to be 1. We just will make one side 1 and the other one side 4. This other side, therefore, is, remember, it's the Pythagorean theorem is a squared plus b squared equals c squared. So 4 squared, 16, is equal to this side, the 1 squared side squared, plus 1 squared. So 16 minus 1 is 15. So we get the square root of 15 is our other side, because 15 plus 1 is 16. And therefore, you have to take the square root of that, because a squared is 15. So a is the square root of 15. All right, well, cool. Well, now that means we can actually do this as the cosine of A, and the cosine of A is the adjacent over the hypotenuse, so it's the square root of 15/4. And that's actually what it is, and it's just an easy way to do it. A couple other things to remind you is that the inverse sine of the sine is always x. So the inverse sine of the sine of x is just x. X in this case, remember, has to be between negative pi halves and pi halves, because you can't, you have to be in that domain. And the sine of the inverse sine of x equals x, again, because you're composing two inverse functions, you should get the thing inside. And in this case, because we want to be able to put it into the inverse sine first, the x value has to be between -1 and 1. All right, So now let's talk about what the derivative of the inverse sine is. Okay. So one of the things I'm going to remind myself is that y is equal to the inverse sine of x. So that's what we have. And what we want to do is try to figure out what this would be. So I'm going to think of first again, I don't like inverse sine, so let's do the sine of y equals x. Okay. So we're going to go ahead and take the derivative of both sides. So the derivative of sine y, the derivative with respect to x of x. Well, this is an implicit function. We don't have y by itself. We have sine of y equals x. We don't have it solved for y. So we have to figure out what to do with that. So looking at that, what it seems like is we can use implicit differentiation. And implicit differentiation tells me that this is the derivative of the outside. The derivative of the outside is sine of something. The derivative of sine of something is cosine of that something. That something happens to be y. So it's the cosine of y times the derivative of the inside. But again, I don't know what the derivative of the inside is. I don't know what the derivative of y is. So the best we can write is dy dx. The other side of the equation was the derivative with respect to x of x, which of course is just 1. So we now know that the derivative of y with respect to x is 1 over the cosine of y. Well, that's nice. That's cool, but doesn't really do much for me. So we're going to do the same thing we did before. We're going to look at the fact that we have a triangle here. Okay. And remember what y is y is the inverse sine of x. So the cosine of the inverse sine of x is what we have. So we're going to basically do what we just did on the other problem. We're going to go ahead and try to simplify this. We're going to say that well, let's just use y. Y is the inverse sine of x. Trying to figure out where to write this. I'll extend the page. There we go. We'll come back up to that. Y equals the inverse sine of x. So that means the sine of y equals x in a triangle, right triangle. If this is my side y, this is my angle y, then I have x just by itself. So again, sine is opposite over hypotenuse. So it's x over, we can call the hypotenuse 1 because x isn't over anything. So we can assume it's 1. Using Pythagorean theorem, 1 squared minus x squared will give you the other side squared. So I took the square root of it. And then I see, oh, well, I want the cosine of y. The cosine of y is the square root of 1 minus x squared over 1. Remember, it's adjacent over hypotenuse. But the cosine was in the bottom. So it's be 1 over the square root. Actually, I'm sorry. No, it's not. It's in the bottom. That's where it's supposed to be. So it's in the bottom, so it's 1 over. And the cosine is adjacent over hypotenuse. The adjacent side is the square root of 1 minus x squared over the hypotenuse, which is 1. So we're just going to get 1 minus x squared. So there is the derivative of the inverse sine. The derivative of the inverse sine is 1 over the square root of 1 minus x squared. Okay. All right. And x, by the way, remember, x has to be between -1 and 1 because that's the domain that we're dealing with. Okay. All right. And actually, it's got to be just great less than because you can't have 0 in the denominator. All right, so we have -1 is less than x is less than 1. So even though the inverse sine domain is -1 to 1, we can't be 0 in the denominator. All right, so let's try a problem. Let's go ahead and do this one. So with the inverse sine of 3x cubed is my function, I want to find f prime. So again, it's an outside and inside function. The derivative of inverse sine is 1 over the square root of 1 minus whatever squared, then times the derivative of the whatever. The whatever in this case is 3x cubed. So we're going to put a 3x cubed inside the whatever in the denominator, and then multiply by the derivative of 3x cubed. The derivative of 3x cubed is 3 times 3 is 9 times x squared. So we end up with 1 over the square root of 1 minus 9 x to the 6th times 9x squared. If you want to put those together, you can. The domain of this, well, now we have to come up with the domain of this. So remember, your denominator needs to be between -1 and 1. So the domain of f, we're looking first at the domain of f. So the domain of f is this 3x cubed has to be between -1 and 1. And including -1 and 1. So -1 is less than or equal to 3x cubed is less than or equal to 1. Well, again, I kind of want to know what x is by itself. So let's go ahead and divide through by 3. So I get -1/3 is less than or equal to x cubed is less than or equal to 1/3. Then if you want to take the cube root of both sides, you can do that. Or we can just leave the answer just like that, and that's okay. So we now know that x cubed has to be between -1/3 and 1/3. Let's do the domain of f prime. The domain of f prime, and again, if you want to do the cube root, you can. But I was fine with the other way. So the domain of f prime is very, very similar, except that we need that the thing under the square root has to be positive. It has to be not 0. Actually, saying it has to be positive is fine. So -1 has to be greater than 1 minus 9x to the 6th, which has to be less than 1. We don't do equal to because it's in the bottom, and you can't have 0 in the denominator. And so we have that. So we're going to go first to go ahead and add the 1 to both sides. So if I add 1 to both sides, I'm going to, or subtract 1 from both sides, sorry, I'm going to get -2 is less than -x to the 6th. -9x to the 6th is less than adding 1 to both, subtracting 1 from both sides. I get 0 over here. And then I need to divide through by -9. But remember, when you divide and an inequality by a negative sign, you have to switch the direction of the inequality. So we're going to get -2 over -9, or 2/9 is greater than x to the 6th is greater than 0, because we divided through by -9. And then go ahead and now we have to figure out what to do with this, because now we have a little bit more work going on here because we've got this inequality and so forth. So we're going to go ahead and say x equals 9/6. I'm sorry, 2/9. And we're going to take the 6th root. So x is equal to plus or minus the 6th root of 2/9. And this is why we need to do it this way, because we're going to have that plus or minus. And then you want to look at the different places. So we've got negative the square root of 2/9, the 6th root of 2/9. And we have positive the 6th root of 2/9. And you want to look to see if it's positive or negative in those different places. So if you put 0 in the middle, because that's where 0 is, you're going to get negative to the left of -2/9. Because if I went ahead and took a number and I raised it to the -2/9, negative the 6th root of 2/9, number smaller than that, like I don't know, -5, probably smaller than that. And I would get a positive number there. And we're going to go back to the original. So we'll go back to the very, very original. Oh, don't forget, we also have x equals 0. So we can't have 0 picking 0, but we're going to go on either side of it. So we can pick a number less than this. We go back up to this original thing here, and we'll go ahead and put those numbers in there. Pick a number that's less than negative the 6th root of 2/9. And when you plug that in there, you're going to get a number that actually is negative. If you pick a number between 0 and -2/9, you're going to get a number that's positive. If you take a number between 0 and positive the 6th root of 2/9, you're going to get positive again. If you take a number beyond that, you're going to get negative, if you put it into the equation here that we're working with. So that means now that my domain is from negative the 6th root of 2/9 to positive the 6th root of 2/9. That's where that denominator would have been positive. And so there you have that information. Let's try a few more things. Let's look at the inverse cosine of y with f x equal to y. Again, that means that the cosine of y is x. In this case, restricted domain is 0 to pi because cosine actually goes from positive to negative between 0 and pi. So we're all good. And remember, x is going to be between -1 and 1. All right. So we're going to find this derivative. We could go through the exact same thing, but it turns out that it's just -1 over the square root of 1 minus x squared. So it looks very, very similar to the inverse sine that a lot of times you won't see us play around with as much because they're going to be the same. So we don't do much with this one, but I wanted you to see it. It looks just like the inverse sine, except it's negative. Remember, cos are negative, non-cos are positive. So it's still having that same kind of thing happening. The inverse tangent of x equals y, or tangent means the tangent of y equals x. Again, we're going to say our angles between negative pi halves and pi halves because the tangent would go positive and negative there. Here, the range is all real numbers. So we don't have any stipulation on that. Tangent can be any number in there. If you look at the graph of tangent. I could go through the same thing of finding out what it is, but I'm just going to tell you the derivative with respect to x of the inverse tangent is 1 over 1 plus x squared. So let's find the derivative of y equals the inverse tangent of x squared. That would be, again, the derivative would be 1 over, this again is a chain rule. We have the derivative of the outside, which is tangent, the derivative of inverse tangent. Then we have inside of x squared. The derivative of inverse tangent is 1 over 1 plus something squared. Then times the derivative of the something. The derivative of the something is 2x, because the something was x squared. So you put the x squared inside that parentheses there with the square, and then you have that derivative. So those are the inverse sine, cosine, and tangent functions. They're derivatives. We don't really deal very often with the inverse secant, cosecant, and cotangent, so I'm not going to do those, but we do see these a lot. And actually, we look more with the inverse tangent and the inverse sine.